It's something we see literally every single day, yet surprisingly few of us actually know the true mechanics behind it. I mean, everyone has stared up at that perfect, vast sky and wondered this exact question at least once, right? Maybe you asked your parents when you were a kid, or maybe you've totally fumbled trying to explain it to someone else. But what's really fascinating here is that the most common answers people give, they're actually completely wrong.
So, Section 1, Busted, Top Sky Myths. Let's get into it.
Let's just clear the slate right out of the gate by looking at what people think causes a blue sky. Myth number 1, the sky is blue because it's reflecting the ocean. Completely false. I mean, the sky was blue way before massive oceans even existed on Earth. Plus, it's the exact same shade of blue over a bone-dry desert. The fun twist, actually, is that oceans look blue partly because they reflect the sky, not the other way around. Myth number 2, the air itself is blue. Nope, air molecules are completely colorless. And myth number 3, well, some cute stories say it's magic or a giant painting, but yeah, physics definitely has the receipts over magic here.
Which brings us to Section 2, the real science, Rayleigh scattering. So what is actually happening up there? The jaw-dropping truth is there's an invisible battle of light waves happening over 10 miles above your head right now. Sunlight might look like a plain white beam to us, but it's really a squeezed rainbow. It's got all the colors packed in, and each color has its own wavelength. Think of them like ocean waves. You've got these long, lazy waves. Those are the reds and oranges. They just cruise straight through the air, no problem. Then you have the short, zippy waves, the blues and violets, and those, they tend to bounce around like crazy when they hit something.
And that bouncing brings us to our core concept. When that squeezed rainbow of sunlight hits Earth's atmosphere, which, remember, is just packed with tiny nitrogen and oxygen molecules, those short, zippy blue waves crash into the air molecules and scatter in literally every conceivable direction. This whole process is called Rayleigh scattering, named after Lord Rayleigh. He's the brilliant scientist who figured all this out back in 1871. The wild math behind this is just brilliant. Because the scattering strength is based on the inverse of the wavelength to the 4th power, shorter wavelengths scatter exponentially more. The end result? Blue light scatters about 10 times more than red light. 10 times! So it's really a matter of scale. Just imagine throwing a handful of ping-pong balls, representing our short blue waves, and a bunch of heavy basketballs, representing the long red waves, through a super dense forest of tiny sticks. The ping-pong balls are going to ricochet everywhere in completely chaotic directions, right? Because they keep pinging off the sticks. The basketballs, though, they just plow straight through unaffected. So when you look up at the sky, anywhere away from the sun, your eyes are just getting flooded with those ricocheting ping-pong balls, that scattered blue light. All right, Section 3, the twist, the purple sky mystery. Now, let's see how this builds into a really fascinating paradox, because I know exactly what some of you are thinking right now. Wait a minute. If shorter waves scatter more, and violet waves are actually shorter than blue waves, why aren't we looking at a giant purple sky every single day? It's a fantastic question. Violet scatters way more aggressively than blue. Well, it turns out physics and biology actually team up to solve this one. First, on the physics side, the sun's emission spectrum just isn't perfectly even. It simply pumps out vastly more blue light than it does violet light to begin with. And second, the biology side. Human eyes are built with millions of color-detecting cones, and we just so happen to have way more blue-sensitive cones than violet ones. So our own biology is practically hardwired to favor the blue. Moving on to Section 4, Edge Cases, Sunsets and Alien Skies. So how does this exact same rule explain why the sky changes colors at the end of the day? When the sun is low on the horizon, its light isn't just shooting straight down anymore. It has to travel through a much thicker, longer slice of the Earth's atmosphere to reach you. And because it's traveling through all that extra air, practically all that short blue light gets completely scattered away before it even reaches your eyes. What survives that long journey? The longer, lazier waves, the reds, the oranges, and the pinks. Toss in a little dust or smoke in the air, and boom, you get those incredibly dramatic, fiery sunsets. And it's so cool to look at how these physics rules apply elsewhere in the solar system. If we compare Earth to Mars, the whole effect completely flips. NASA rovers confirmed that because the Martian atmosphere is just loaded with larger iron-rich dust particles, Mars actually has a butterscotch-colored sky during the day. But when the sun sets on Mars, the light travels through the dust in such a way that the sunset itself is a glowing, stunning blue. Literally the exact opposite of Earth. Honestly, this scattering rule dictates practically everything we see when we look up. Go to space? The sky is black. Why? No atmosphere, so absolutely no scattering of light. Climb to a massive mountain peak? The sky becomes a much deeper, darker blue because there's just less air above you to scatter the light. And clouds? They're white because they're made of giant water droplets, which are so large they actually scatter all colors of the rainbow equally, mixing them right back into white light. Which brings us to Section 5, Actionable Proof. Try this at home. Because, hey, you don't have to just take my word for it. You can actually recreate this exact atmospheric physics phenomenon right in your own kitchen. If you want to see this with your own eyes, all you need is a clear glass of water, just 2 or 3 tiny drops of milk, a flashlight, your phone light works perfectly, and a dark room. It's a 60-second experiment, but I promise it absolutely blows people's minds. Here's the whole shebang. First, stir the milk into the water until it looks just a little cloudy. Those milk particles, they're gonna act like our atmospheric molecules. Next, turn off the lights and shine your flashlight directly into the side of the glass. If you look at it from the side, you're gonna see a distinct bluish glow. The milk particles are scattering the short blue light waves right towards your eyes, perfectly mimicking the daytime sky. But if you physically move and look straight through the opposite end of the glass, directly at the light, the water looks reddish-orange. You literally just created a sunset in a glass because the blue light scattered away, leaving only the long red waves to reach you. This little home experiment is a perfect example of what we call the Tyndall effect. It's the scattering of light by particles in a fine suspension, like our milk in the water. It was actually first noticed by a guy named John Tyndall, who figured out the initial steps of this whole phenomenon before Lord Rayleigh came in later and nailed down the exact mathematical formula for the atmosphere. So the absolutely crucial point to take away from this explainer is that understanding why the sky is blue does way more than just win you trivia points at the bar. It connects you directly to the elegant rules of the universe. Every single time you look up, you are literally witnessing tiny atmospheric molecules dancing with photons of light in perfect mathematical harmony right above your head. And when you realize that distant, undiscovered exoplanets across the galaxy could have skies of vivid green, deep orange, or even brilliant purple, depending entirely on the unique gases floating in their atmospheres, well, it really leaves you with one final thought. What other spectacular scientific secrets are hiding in plain sight, just waiting for us to look up and ask why?